So, what if I told you that basically everything you think you know about how the world works is wrong? Seriously, we're about to dive into the foundations of quantum theory, and it all starts with one kind of radical idea: your physical intuition. The stuff you've learned just by living your life, it completely falls apart when we look at the tiny, fundamental building blocks of our universe.
And hey, that's not just me saying it. That is a direct quote from a university physics course. It's really the perfect place for us to start. See, we're not just adding new facts to what you already know. We are actively trying to unlearn our old classical way of thinking. So let's just clear our minds and get ready to rebuild our understanding of reality from the ground up. All right, so the first major cracks in that old way of thinking started to show up with a really simple question about energy. It seemed like it should be easy to answer, but classical physics just couldn't get it right. I mean, think about a piece of metal in a forge. As it gets hotter, it starts to glow red, then orange, then white hot, right? That light we see is just energy being radiated away. Well, scientists tried to come up with a formula to predict exactly how much energy would be radiated at each wavelength, or, each color. The problem was, their formula completely broke reality.
And when I say it was wrong, I mean it was spectacularly wrong. The classical prediction said that as you looked at smaller and smaller wavelengths, moving into the ultraviolet spectrum, the energy being blasted out would shoot up towards infinity. They actually called it the ultraviolet catastrophe. But of course, that's not what happens. We don't get vaporized by infinite energy every time we turn on a hot stove. The real world, thankfully, is much better behaved.
So, how did they fix this? Well, a physicist named Max Planck came up with this really wild idea. He basically asked, what if energy isn't some continuous smooth-flowing river? What if it's more like a stream of tiny individual packets? He called these packets quanta. And with just that one simple, really strange rule, the math suddenly worked. It was perfect. The catastrophe was gone.
And here's the kicker. This wasn't just some one-off trick to fix a single problem. This idea of energy packets turned out to be the master key that unlocked another totally baffling puzzle, the photoelectric effect.
Okay, so this is the thing that happens when light hits a piece of metal and knocks electrons loose. Now, the old classical theory, which saw light as a wave, made some really clear predictions. A brighter light is like a bigger wave, so it should hit the electrons harder and knock them out with more energy, make them faster. But that's not what happened. Brighter light just knocked out more electrons, not faster ones. If you wanted faster electrons, you had to use a higher frequency light. Think blue light instead of red. Well, Einstein's quantum solution was just brilliant. Light itself is made of these packets, which we now call photons. Brighter light just means more photons are hitting the metal. But the energy of each individual photon is all about its frequency. A single low-energy photon of red light might not have enough oomph to knock an electron loose, no matter how many of its buddies show up to the party.
Okay, so the evidence seems pretty clear at this point, right? Energy comes in packets. Light is made of particles called photons. The old wave theory is out. Case closed. But this is where reality gets much, much stranger.
I mean, this feels like the logical conclusion from everything we've just seen. You've got the black body problem, you've got the photoelectric effect. They both point directly to light behaving like a stream of tiny little bullets. It feels pretty settled.
But then you do this famous experiment. You shine light at a barrier with two tiny slits in it. Now, if light were just particles, like little paintballs, you'd expect to see two bright lines on the screen behind it, right? One for each slit. But you don't. You get a whole series of bright and dark bands. This is called an interference pattern, and it's the classic telltale sign of wave canceling each other out and adding together. So, wait a minute. Suddenly light is a wave again?
All right, fine. So light is having a bit of an identity crisis. We can let that slide. But what about stuff? Things we can touch. Electrons, the things that make up atoms. I mean, those are definitely particles. Our intuition just screams that tangible things have to be solid, predictable little balls.
And this might be the single most mind-bending result in all of physics. If you do the exact same double-slit experiment, but you fire electrons one by one, something that seems impossible happens. Each electron lands on the screen as a single dot, just like a particle should. But as you let them build up, over time, they arrange themselves into that exact same wave-like interference pattern. It's as if each electron somehow knows about both slits at once and where all the interference bands are supposed to be. Matter, just like light, acts like both a particle and a wave.
So what's the big takeaway from all this? It's not that light and matter are secretly both a wave and a particle. It's that our everyday labels, our classical concepts, are just not good enough. They're approximations. The fundamental nature of reality is something else entirely, something our language just wasn't built to describe.
And this all-or-nothing behavior doesn't just apply to energy or whether something's a wave or a particle. It turns out to be a fundamental rule for all sorts of other properties of the universe, too.
So in this experiment, scientists fired atoms through a magnetic field. Now, classically, you'd expect their spin, you can think of it like a tiny spinning top, to be pointing in any random direction. So when they pass through the magnet, they should be deflected by random amounts, creating a continuous smudge on the detector screen. But what they saw was astounding. The atoms only ever hit two distinct points. Their spin isn't a continuous value. It's quantized. It can only be up or down, with absolutely nothing in between. It's yet another fundamental property of our universe that comes in discrete, all-or-nothing packets.
So, okay, let's take a breath. We've seen the old rules just fail spectacularly. Energy isn't smooth, matter isn't just particles, and properties aren't continuous. So, what are the new rules of the game?
Let's recap what we've learned. First, quantization. A lot of things we thought were continuous, like energy and spin, can only exist in these discrete, separate amounts. It's like reality has pixels. Second, duality. The classical ideas of wave and particle just don't cut it. Reality at the quantum level is some kind of hybrid of both. And finally, and this is a big one, probability. We can't actually predict with certainty where a single electron will land. All we can know is the probability, like rolling a loaded die. The universe, at its core, isn't a perfect clockwork machine. It's a game of chance.
And, this isn't just some abstract philosophy. That weird quantized property of spin, the fact that it can only be up or down, that is the exact principle we use to create quantum bits, or qubits. The entire revolutionary field of quantum computing is being built directly on top of these bizarre, intuition-defying rules of reality.
Which really leaves us with one final, kind of tantalizing thought. For centuries, we built our entire world on the rules of classical physics. But now we know the real rules of the universe. So the question is, as we start to really master them, what are we now capable of building?